So let's take an example of one of these targets and see how that would inform us about the survey lines, the shape of the actual grid. So let's say that we have a 250-pound object that we're looking for at 50 feet. So I'm going to redraw that information here at the top. So 250 pounds equals 1 nanotesla at 50 feet. Now, what we want to remember as we're doing this is that we might actually be able to see quite a bit larger signal from this anomaly that we're working with. In general, we do a survey grid, which means that we are going one direction, turning around, and coming back. Now, I'm drawing this as though it is a marine survey, but the same holds for all types of land and airborne surveys. The fact is that we can see 1 nanotesla at 50 feet. So if we were to say that a 1 nanotesla anomaly was the minimum amount, and that since we don't really know what the history of the object is, so we don't know if it was magnetized during its formation, or perhaps it was impact demagnetized when it hit the surface of the water, or it has partially demagnetized over time due to chemical means. We're not sure. So we can't absolutely count on this. We don't know, in fact, that it has a volume amplifier or that it maybe has an aspect ratio amplifier. We suspect that these may be in play, but let's take the worst case scenario and just work with 250 pounds at 50 feet. So what would be our survey grid? Well, what we normally do, there are two ways of presenting this data. One is to stack the profiles. So this is line A, this is line B, C, and D. And essentially we can stack the profiles, and what we see is that this would indicate to us that the object is somewhere in between A and B. The reason is that we get further away, we have trouble seeing it, or that the amplitude gets lower and lower, and I'm just giving these relative amplitudes. If we cannot see it from both lines, when we end up making a contour map, which would look something like this, if the object is too small to be seen from both lines, and in that case we would have a situation like this where we wouldn't see it very much at all on A, and then B we would see it, it's a very small thing, and then we don't see very much on C, then we really don't know where it is. And in fact, when we end up making a map, there's only one solution for us, and that is to actually put it on line B, because that's the only place we saw it. And we don't really know whether it's on the line, or to the left, or to the right. We don't know whether it's over here, or whether it's over here, because we can't really see it on those other lines, and therefore we don't have any information about how it might be positioned. All we can do is put it on the line because we saw it on that line. But the transverse gradiometer improves this by giving us the slope of the magnetic field along the line. And so if we tow a sensor array where we have one sensor, and then we have a second sensor, and we are towing a transverse gradiometer, TVG, where we have a separation here of perhaps 1.5 meters, then even if we only see it on one line, we immediately know whether it's on the left or the right, because we'll be getting dual lines, and one of these lines will have a slightly greater amplitude than the other one. So this one might be a bit bigger, and this one might be a bit smaller, and so we know in fact that the object is to the left side of the line as we were going forward. So the transverse gradiometer gives us the ability to better place anomalies on the map. It also gives us the ability to see a little further out between the lines so that we are able to make more efficient use of our survey time. Now, the distortion of the Earth's magnetic field we were talking about earlier, and I'll just redraw that briefly. When we get an object, we get a confluence of the Earth's magnetic flux lines on the south side and a spreading of the Earth's magnetic flux lines on the north side, which gives us a positive to the south and a negative to the north on lines that pass over the anomaly. But this distortion that I'm drawing in 2Ds, in 2D space, really takes place in 3D space. So that means that if we're towing this array over the seafloor, we not only have the side-to-side distortions that we're looking for, but we also have a maximum distance that comes into play here. So in this case, the anomaly that's associated with the object will be roughly equal to its depth if we are making maximum use of our towing ability.